Hi, so in our book in section 5.4, we start putting together the ideas of first derivative and second derivative and what that means for graphing. And I wanted to actually in this video go over just what kind of questions we're going to see in the homework and maybe the best way to practice the homework questions. So the first thing that I have here is question 1. And so what you'll see is that you're not actually filling out a lot of information, but I do want you to be able to find the things that are mentioned in here. But in my lab, lots of them, it just says like pick the graph, that kind of thing. Here it also asks you to find the derivatives. And I know you could just like plug these into Desmos or a graphing calculator to go ahead and get the graph, but I really want you to use these problems to practice finding the first derivative, using the first derivative to find increasing, decreasing maxes and mins, and then use the second derivative to figure out where the function is concave and concave down, or concave up and concave down, and then it's like putting those two things together. What does it mean if it's increasing or decreasing, concave up, concave down? What happens when we put it together with the graphs? Okay, so first thing is here, number 1, what I want to mention, I think it's going to be the case for any of the homework questions here, is that it's going to be hard to find the x-intercepts. So go ahead and skip that step. And then just try to use the other information, first derivative, second derivative, to find that stuff that I was talking about. But go ahead and skip that because it's not quadratic, which means you can't use the quadratic formula to set it equal to 0 and find x-intercepts. And things like factoring by grouping isn't going to work with a problem like this. And the same is true for number 2. So for this one, you can also go ahead and skip the x-intercept. And just to recap, the x-intercept is when you set the original function equal to 0. I will say for either one of these, and this goes for, same thing for number 3 here as well, skip that. So while for all of these problems, I'm asking you to skip the x-intercept, I am going to show you an example of one where you can find the x-intercept. Just right here. So again, that's setting the original function equal to 0. So even though I'm saying to skip that in all 3 of these questions, you can, in either case, find the y-intercept. Because the y-intercept is just when you plug in 0 for x. So like if I did this for number 3 here, for this particular function that I'm given, that gives me -2. So at least then I know one point on the graph in this case is 0, -2. And if you were trying to select the right graph, that does give you a little bit of information in that, okay, it could be this graph, not that graph. It could be this graph, not that graph. But I don't want you to treat these problems as just kind of guessing which one will be the right answer, because in theory, I want you to be able to take a function and be able to find all that information to construct a graph on your own. It's just the homework software doesn't really allow for you to do something like that. Okay, the one that I want to look more closely at in this video is number 4. And the reason I want to go over number 4 is because I think it's a great example to look at how to put all of these pieces together in terms of constructing a graph. So let's go ahead and take a look at that. So first we could find the x-intercept, which means we set the function equal to 0. And to set it equal to 0, I can go ahead and factor. In this case, I'm going to factor out 2x cubed, which leaves 2x minus 3. Then you can set each part equal to 0. Okay, so we've got 2 x-intercepts. So what this tells us about our graph is we've got an ordered pair, 0, 0, and 3 over 2, 0. And these will be 2 points on the x-axis. I'm also going to go ahead and do the work to show how to find the y-intercept here, but it is a little bit redundant because we've actually already found it. And that's because what can happen sometimes is if you get a 0, 0 answer from the x-intercept, that's also going to be the y-intercept because there's 0 for the x and the y. So here, this is both an x and a y-intercept. And if we're thinking ahead a little bit about what we'd expect from our graph, I might even start to draw a little bit of a sketch here. So it's going to go through a point here, the origin at 0, 0, and 3 over 2 is about 1, or not about, 3 over 2 is 1/2, so I can put another point right here. So that's where our graph is going to cross the x-axis. Now let's go ahead and start taking derivatives. So first let's find the first derivative, f prime of x. And remember that we use the first derivative to figure out where the function is increasing or decreasing, and we also use it to figure out if there are any relative max or min values. To take the derivative here, we can pretty much use the power rule. So we get 4. The derivative of x to the 4th is 4x cubed minus 6. The derivative of x cubed is 3x squared. So our derivative is 16x cubed is equal to 18x squared. So what we do a lot of when we're using the first and second derivative is set them equal to 0. So if we were dealing with the original function that gave us the x-intercepts, when we do that with the first derivative, that's how we find critical numbers. So to set this equal to 0, I'm going to go ahead and factor. So here I can factor out 2x squared. And then I'll set each piece equal to 0, each factor. So we get x equals 0 and x equals 9 over 8. So it can't happen here. I mean, this is an x-intercept, a y-intercept. Now it's also a critical number. So what we're going to do at this point is I'm going to draw a number line. And I like to label them, so especially when I'm starting to put together first and second derivatives to try to sort of keep everything straight. So I'm going to label it as a first derivative, so I know that this is when I'm trying to figure out increasing, decreasing. I'm using the first derivative, and when I plug things in, I'm going to be plugging them into the first derivative. So I'm going to put the numbers, any critical numbers here. So I've got a 0 and a 9 over 8. And with this number line, you treat it like any number line, which means it has to be in order. So smaller numbers go on the left, bigger numbers go on the right. And at this point, what I want to do is just choose any number in each interval. In this case, I have 3 intervals. I'm going to choose any number in that interval to plug into the first derivative. So for the first interval, I just need anything less than 0. I'm going to go ahead and just plug in -1. Between 0 and 9 over 8, I can actually plug in 1, falls between those two numbers. Anything bigger than 9 over 8, I'll go ahead and plug in 2. So you have a couple of options here. One option is that you just plug it into that entire derivative function. So I could say here, since f prime of x is, if I do it this way, I usually go with the non-factored form, 16x cubed minus 18x squared, and just plug it in here. So -1 cubed, it's going to stay negative, where squared, -1 squared is going to become positive. So that's negative 16 minus 18. So we get negative 34. And the 34 part really doesn't matter. What we're trying to figure out is it going to be positive or negative? And we found out that in this interval, the derivative is going to be negative. So I'm going to draw a negative right here. The other way that I was going to show is that you can also figure this out by looking at the factors here and just seeing that if when you plug it in to the factors, if you end up with a plus or a minus. So like, for example, I can sometimes write the factors up here. So I have 2x squared as one of them and 8x minus 9. And so I can take the negative 1 that I was just talking about. If I plug it into 2x squared, well, no matter what I plug in there, that's going to be positive. If I plug a negative 1 into the second factor, I would have negative 8 minus 9, which is negative. So when you think about when you multiply a positive times a negative, the answer is negative. So that still gets you to that result that in that interval, the first derivative is negative. And let me keep going. And I'm going to keep going by not plugging it in using that first method. I'm going to use the two factors up here. So let's say if I plug in a 1, 2x squared is always positive. 8x minus 9 is going to be 8 minus 9, which is still negative. A positive times a negative is negative. And then going to 2, 2x squared is always positive. 8x minus 9, if I plug in a 2, is going to be positive. So positive times positive is positive. And then at this point, what I like to do is like try and visualize what's happening. So if the derivative is negative, that actually means the original function is decreasing. So I might draw something to kind of remind myself, okay, the graph decreases, and then it actually continues to decrease, and then it increases. And so at this point, I also might think about any relative max or mins. So there's actually no relative maxes here, but I can see that there's a relative min right here at x is equal to 9 over 8. So what I'm going to do now is I'm actually going to go to the second derivative, so I'm just going to hold off. Although maybe I would go ahead and you could even write the increasing, decreasing stuff here if you wanted to. So maybe I'll just do that as a recap of for sections 5.1 and 5.2. So I could write this and say, okay, my graph is increasing. The interval starts at 9 over 8, and then it just keeps going to the right. So I would say to infinity. For decreasing, I think you can write this one of two ways, since 0 is actually included in the function. There's not a vertical asymptote or anything there. I think you could write it and say it's, let me change the colors here. This is the biggest number, and then everything to the left. So from negative infinity up to 9 over 8, the graph is going to be decreasing. But it would also be okay to write it and just skip over the number 0. Something's sort of happening at 0. We'll talk about it later once we look at concavity. But it's kind of like it slows down and it's not technically decreasing at 0. It's sort of flat, and then it starts to decrease again. So that's why we have this behavior for this graph where it looks like it's decreasing on those two intervals that are right next to each other. And then no relative min. Oh, I'm sorry, I meant to say no relative max. That there's a relative min at x equals 9 over 8. And if I wanted to figure out where that relative min is located, like what is the relative minimum, then I could take this value and plug it into the original function, f of x. And so the original function is right up here. And maybe I will go ahead and just plug that in. use my calculator for this part. So if I plug it in and convert it to a fraction on my calculator, I get this. If I wanted the approximation, like especially if I'm trying to draw a sketch of the graph, I might go ahead and get the approximation, just so I have an idea of where to plot it. And it's about negative 2.1. And you could do the same thing with 9 divided by 8. So it ends up being 1.1 about, and then negative 2.1. So if I wanted to add to my kind of sketch that I have started here, I could go ahead and plot this point, about 1.1, and negative 2.2 would be a point right about here, is where I would expect there to be a relative min in my graph. Okay, but now let's go ahead and look at the second derivative. So first let me rewrite the first derivative again, and I'm going to write the non-factored form. So that was 16x cubed minus 18x squared. Now let's take the second derivative, which just means take the derivative again. Okay, so for the first derivative, what we're looking for is whether it's going to be concave up or concave down, which means like that or that. The way we do that is what we've been doing a lot already, which is set it equal to 0. And to set it equal to 0 here, I'm going to go ahead and factor. Okay, so both of these are divisible by 12. So I'm going to factor out a 12x. And then it's going to be 4x minus 3. Set each piece equal to 0. And we get that x is equal to 0 again. And then we also get x is equal to 3 over 4. Now, since we're dealing with the second derivative, what we call these are points of inflection, or inflection points. And we're going to do the same thing with the number line, but we're going to deal with the second derivative instead, but we're repeating the same process here that we did with the first derivative. So I'm going to draw the number line, I'm going to put my inflection points on there. I can pick any numbers in either interval. So here I can't pick 1, so maybe I might pick something like 0.5 or 1/2, and then I can pick 1 in the last interval. So I'm going to go ahead and use that method again where I write the factors. This method only works if you write all the factors down, even if there's just like a coefficient in the front, because it might change the sign of the problem, and so you wouldn't want to forget about it or leave it out. Okay, so if I plug in something like -1 here, 12x is going to be negative. 4x minus 3 is also going to be negative. Negative times negative is positive. If I plug in something like 1/2, 12x is going to be positive. If I plug in 4x minus 3, if I plug in 1/2, we get a negative. And then finally 1. 12x is 1, and 4x minus 3. Or not 1, positive. 4x minus 3 is also positive. So I didn't finish writing that, but for the middle interval, positive times a negative is negative. Positive times a positive is positive. So here's where I also like to think about the visual. And so what does that mean? We're dealing with the second derivative. Positive here means concave up. So that means in this first interval, it's going to look like that. Second interval is negative, so concave down, and then concave up again. now is when we really want to try and put it all together. And so what I typically do is I'll draw another number line. And I'm going to try and figure it out for the whole graph of f of x, which is different from what I've done before. And I'm not actually plugging in anything at this point, but what I do on this number line is I put all critical numbers, all inflection points. If there's a vertical asymptote, I'd put that on there too. And so what do we have? Well, we had the number 0, and then we've got 9/8 and 3/4. So 3/4 is smaller than 9/8, so I need to make sure to write it in the correct order. So these are all our intervals. So first I'd actually go back to the first derivative. Okay, so basically it's decreasing all the way up to not negative, 9/8. So what I'm going to do is I'm going to indicate that. So it goes decrease, 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 and then after 9/8 it's increase. And I'm going to do the same thing looking at concavity. So let's see, it's concave up less than 0, so that's going to be right here. It's concave down between 0 and 3/4, so I'm going to put a concave down symbol, and then it's concave up after that. So concave up, concave up. Now, like putting it all together is like, what does that look like? So if I look in that first interval, like less than 0, what does it mean to be decreasing and concave up? Well, if you look at the concavity, whether you're looking at concave up or concave down, it's half increasing and half decreasing. So in this case, it's going to look like the part where it's decreasing. So if I highlight that part of concavity, so that tells me the graph on the interval is not only decreasing, but it has this shape to it. And then I go to the next interval. Okay, so now it's decreasing concave down. So I have to find the decreasing portion of concave down, and that's this part right here. So that means my graph is going to look like this in that interval. That's going to be the shape of it. So I keep going. Now I've got decreasing and concave up again. So that means it's going to be kind of this left side of the concave graph. So it's going to look like this. And then finally it's increasing and concave up. So we need the increasing part of concave up, so it's going to look like this. So the last step is to put this all together. So if you want, you could plot extra points. I've already plotted a few points on my graph already, but now it actually becomes like a connecting the dots type of problem, which is where I just need to connect it and have these shapes in each part. So let me go ahead and put the graph that I already drew, and I'm going to put it right here so we can see it all at the same time. Okay, so now let me try to put it all together. So in this case, let me start with less than 0. I just need to draw this shape. So I'm going to draw it as decreasing and concave down up to that point 0, 0. Then between 0 and 3/4, so 3/4 is smaller than 9/8, so I might just think about it as being less than that point that I have down there. I'm going to try and draw something. I might want to zoom in a little bit here. I'm going to kind of draw this shape, right? Decreasing and concave down, but then it switches to decreasing and concave up. Let's try and switch colors again. So like it changes to this shape, but right between 3/4 where I'm sort of at and 9/8, so then it kind of does something like this. And that last bit, I need that shape. So that'll just continue with that shape, and then it'll look like this. So what's one thing that's happening that I kind of wanted to talk about, that 0, 0 point, which is right here, is just to kind of show you that it's decreasing the whole time, but it's sort of the way that it's decreasing. It's decreasing and then it sort of slows down, and then it starts decreasing more rapidly again, and then it starts to slow down again, and then it starts to increase, is really what's happening with this graph. So hopefully that helps with putting it all together. And I do think that it's a good idea with these types of problems is that once you've done all that work, I think it's great to use a graphing calculator or a program like Desmos to just type it in to see if your sketch of the graph kind of matches up with what you would get in that graphing calculator. I will say something too about homework question number 5. So this one's a little different because it's a fraction. And a review of some of that is that when you set this bottom part equal to 0, it's going to be a vertical asymptote. And so if that ends up being what looks like a critical number or point of inflection, it's technically not because it's actually a vertical asymptote there. The graph is not defined. But when you go to draw like your first derivative graph, and let's see, when we set this equal to 0, that's going to be x is equal to -2/5. That's always going to be on your line for both the first derivative and the second derivative. Because even though it's not a point on your graph, it's a vertical asymptote, it's still a place where the graph can change from increasing to decreasing or vice versa, and it could also change concavity there. So that's why we need to put them on the number lines, regardless of that we might not call them a critical number or a point of inflection. And sometimes to just help me remind myself that that's the case, on this number line I might even draw something that kind of looks like a vertical asymptote to tell me that that's different than, it's not going to be a point that I plot on my graph, but it's trying to look on either side of that vertical asymptote to figure out what's increasing, decreasing, or the concavity. All right, the other thing I'd like to mention is the last question on the homework, which looks sort of overwhelming at first. The idea of this question is that you don't actually have to take the derivatives, but you're given the information already. And what I would recommend doing here is trying to write them on the number line that you're used to seeing to make sense of the information. So it's saying it's, continuous everywhere except at x is equal to 2, where it has a vertical asymptote. And so there is going to be a vertical asymptote at 2. It looks like all the graphs here have a vertical asymptote at 2, except not this one. So you could eliminate a graph based on that. But what I want to focus on is like this is saying the first derivative is positive. So if you think about the first derivative line, it's saying it's positive everywhere. And there might be other critical numbers. I don't know. I mean, I could put, like I was saying, the vertical asymptote on here. But basically it's saying it's positive everywhere, which is the same thing as saying that it's increasing everywhere. So I might convert that to how I would see it as a number line, and it's saying that the graph is always increasing. And this is actually enough information to be able to get the final answer, but I want to go and draw the second derivative line as well. So the second derivative, it's telling me there's 2 intervals where it's positive and 2 intervals where it's negative. So the numbers where it's changing, like the 2, 3, 5, those are going to be my points of inflection that I want to put on the graph. So let me put them in order. So I've got 2, 3, and 5. And again, like I was saying about that vertical asymptote, I might put a little vertical asymptote symbol here to remind myself, okay, that's not a point of inflection, but I'm still going to have it on my number line to figure out concavity here. And then it's saying that it's positive less than 2. So I'm going to put a plus here. And it's positive between 3 and 5. So between 3 and 5, I'm going to put a plus. But it's negative 2 to 3 and bigger than 5. So here's what I have for concavity. And now I might put in the visual, which is positive means concave up, and then concave down, concave up, and concave down. And so I could take these number lines and try and put it all together like I had done in that other problem. And so all the numbers we've got are 2, 3, and 5. Again, I might indicate that 2 is actually a vertical asymptote. And let me just fill in the same information. So it's always increasing. So let me draw that in. And then let me draw in the concavity. So concave up here, concave down, concave up, concave down. And putting that all together, okay, so increasing and concave up means that side. So it's going to look like that on that interval. Then increasing and now concave down means we'd want that left side of concave down. So our graph is going to look like this. And then it's going to look like this. Then it's going to look like this. So we'd want to put all of those pieces together if we were trying to graph it. And you could even try to do like a little sketch, I guess, if you try to put it all together, saying the graph is like this and then that. Oh, I guess I was talking about that vertical asymptote and then I kind of ignored it. But basically it's like going to look something like this. And then it's going to look something like this, and then this, and then that. It's going to curve again. So this is like a really rough sketch that I have here, but then I might look at the graph options and see which one matches. And the reason I said that you could figure it out before even looking at the second derivative is that if you look at two of these graphs, you see that the function is decreasing to the right of that vertical asymptote, but were given the information that it's always increasing. So that leaves us this answer here. And if you look at kind of those curves to the right of the asymptote, you kind of see that shape that we were expecting. So for whatever reason, it kind of has that sort of wavy aspect to it on the right of that vertical asymptote. So anyways, I hope that helps with this section 5.4 and kind of putting all of it together, what we've learned in the first three sections of this chapter.